This is a PCB layout review video of a STM32 board designed by someone who never designed any board before. So this is his very first PCB. I have already done the schematic review of this board. If you haven't watched the video yet, you can do so after finishing this one. The link is in the description. So, is the PCB going to be good? Let's see. Let's have a look at the layout. And before we start talking about this, I would like to see 3D model. So I'm going to open it. And this looks actually quite cool. But, can you see it? Can you see these connectors here? I'm going to open documentation about Arduino. And notice this short connector is actually on this side of the board. And this long connector is on this side of the board. So when I asked the guy who was designing this board why it is done this way, he told me that he was worried that this part of the board could be in conflict with this part of the Arduino, especially this USB connector is very tall. So basically what he did, he placed this side here, sticking out of the Arduino. But the question is why? Because, we are not designing this board to plug it inside of the Arduino. Why we would like to do that? Why we would like to connect this microcontroller with this one? There is no really benefit doing this. So basically, we are designing this board to be a replacement for Arduino board. So in our board, in this board, we should follow the exact shape, exact position of the mounting holes, and exact position of these connectors and pinout. We should have it exactly same on our board as it is on the Arduino. As we have it now here, basically this board is kind of useless. Okay, we can test the circuit, what we are designing, if it works or not, but we can't really use this board as a replacement for Arduino because many people, they design whole systems with Arduino. For example, they design the enclosure. So the Arduino is in a box, and in the box you need to have exact position for the mounting holes. The box will have the shape which is exactly based on the Arduino board, and we will not be able to fit or mount this board there. So I think this is kind of the biggest mistake which is in this design. If I would be designing this board, I would do it compatible with Arduino. Okay, and the second thing what I immediately noticed was this switch, which is huge. Very similar as the tall USB connector on the original Arduino. This can be a problem for the boards if you would like to plug some additional HUDs on the top of this board. This could be big problem because of the height. And also when we are designing boards, very often we need to consider the size and the thickness of the board. Ideally, we would like to make as small board as possible. Every client will tell you, make it as small as possible. Why? Because, you have to pay for the PCB. PCB can be very expensive. And also, small things, they look cute, they are very practical, and that's why, if it is possible, we would like to keep the board as small as possible, and it includes also the height of the board. Okay, so if it's not really needed, then don't use these very tall components. And I'm very, very sure there are switches which can be used here, and they will be much smaller. But I guess, you know, he didn't really have much time to spend in designing this board, so maybe he just used the first switch he found. But to say something positive, I noticed these headers, they have names, so very good. And also this switch, you can see he placed some text to tell everyone who is using this board, to tell them what the position of this switch means. So for example, when the switch is here, this probably means that the board is going to boot in boot mode, and if we move this here on the other side, then this will be standard booting. What I would do maybe a little bit differently is this. I would like to include information how these jumpers can be used, because this is the header for jumpers, and without using documentation, without looking into schematic or, you know, reading this PCB layout, everyone should know how to place these jumpers. So I would put here a text like maybe USB or external, so everyone knows that when jumper is used between these two pins, it will be powered from USB, and when a jumper is used between these two pins, it will be powered from external power. This is also kind of unusual. I don't really do it this way. Notice this text, they are using opposite directions. So I try to have all the text with only two directions, like this or this. But this one and this one, basically, if you would like to read all the text, you only need to rotate board in two directions. But if you use it like this, you may need to rotate it all the kind of directions to be able to read all the text which is here. Okay, so be careful when you are placing text. Maybe you would like to, instead of placing user here, place it like here, rotate it same way as the UART. Also, the size of this text is very small. Sometimes you need to use very small text because there is no space, but this is very large board. There is a lot of space. It's not really necessary to use so small text, so I would use maybe a little bit bigger text. I really like he placed the LEDs together. Some boards, they have LEDs all over, but you know, sometimes if you would like to make enclosure box for this kind of board, then these LEDs, if you have them, if one LED is somewhere here, the other LED is somewhere here, it doesn't look nice on the box. So I really like he kept the LEDs together. I don't know how close they are. Maybe I would put them a little bit further, because when you are making the holes, you don't want the light going from one LED to the other hole, but this is just like very small detail. What I really miss on this board is project name or board name, board version, and maybe also the year when this board was designed. Especially the board version is very important. You will have a number of different versions of your board, and always when you pick one and you are going to do some experiments, or you are going to work with this board, you would like to be sure you are working with the latest version of the board. And you know, sometimes differences between different versions may be very small, and if you don't place here the name or the version, you can make mistake. By mistake, you can work with all the version of your board. You don't want to make this kind of mistakes. Also, you would like to tell others that, oh, this is my board, you know. So place the board name, version, and maybe year and copyright somewhere on the board. Here is a lot of space for this kind of information, so just put it here. Okay, so I think this is everything for 3D. I can close this and we can talk about layout. The very first thing what I noticed when I opened this layout is how much free space is there, but the tracks are still routed very close to each other. And I think this is like one of the most common mistakes what I've seen on many PCBs. Always, when you have free space on your board, spread the tracks. Okay, so instead of routing the tracks like this, move it away from each other, like this. Why we would like to do it? Do you know? Because there is something what is called crosstalk. If you would like to learn more about crosstalk, I have created a number of videos on this topic, so have a look. But very simply to explain, if there is a signal running through this track, then this signal will create fields. And these fields can then influence the tracks which are routed close to this track. And the influence, it means they can create noise on these tracks which are here. Sometimes this noise can be so high that it can change level on these tracks. And this is one of the most common problems why your board may behave randomly. So for example, your board may randomly freeze or reset, or the data are completely random, or you receive random interrupts. This is one of the reasons, because you have crosstalk between tracks. And the easiest way how to eliminate or minimize this crosstalk is to move the tracks away from each other, keep distance between them as big as possible. Okay, this is very important, especially if you have boards. There is a lot of empty space. Don't route tracks like this. Before we continue with this layout, there is one very important thing what I would like to mention. When I was sending this board to production, there were problems. And problems were both bill of material related. So what happened? I'm going to show you. When we go to schematic and when we try to synchronize schematic with PCB, then you will see there are differences. This should not happen. When you are sending your board to production, then schematic and PCB, they should be synchronized. There should be no differences. Luckily, when you have a look here, there are no electrical differences, so the connections, they are okay, but all the differences are in designators. So basically what happened, you can see that he renamed some of the components directly in PCB. For example, he changed the reference designator of this header. He changed it from U4 to SWD. This is not how it should be done, okay? If you need to name your connector or some other components or LEDs in your PCB, you need to use text, okay? You must not change, you must not manually change the reference designators, because when I'm sending files to production, then these files, they include reference designators. The BOM, bill of material, it includes reference designators. Pick and place machine file, it includes reference designators. And if these reference designators are different between schematic and PCB, then PCB manufacturer, they can have problems to find out where to fit specific components. And that's exactly what happened. Basically, when I received these boards, some of the components were not fitted, so I had to fit them manually. Okay, be very careful. Never ever change manually reference designators in PCB. What I really like, he routed most of the signals on top layer horizontally, and most of the signals on the bottom layer, this blue layer, are routed vertically. This is very good approach. Many people starting with layout, they actually try to connect signals on one layer only. And then basically very often what happens, you connect half of the signals, and the second half is going to be very difficult to connect. You may need to place multiple vias on one track to be able to connect the pins together. If you use this horizontal vertical or horizontal vertical routing, you usually need like one via on each track. Okay, you can even see it here, one via on each track, and you are able to connect everything. So I'm very surprised he actually recognized that this is very important, and he used this horizontal vertical routing. What I would do in my design, I would assign colors to some of the nets, especially to ground net. And I'm going to explain, because in this board, I can see this is a 4-layer board. Yeah, you can see top layer, bottom layer, this is layer 2, and this is layer 3. And if you have a look on layer 3, when I select this, this is ground. So all this is ground. There is ground all over the board. If I go on layer 3, this is 3.3 volt power. Okay, there is 3.3 volt power all over the board. Why this is important, or how this can be useful, do you know? So if we apply color on ground net, because there are many ground pins, you will immediately see which of these pins you don't really need to worry. And you don't need to worry about them because connection of the ground pin is very simple. It will be only short track and a via. So suddenly your board is, or the layout of your board will become much easier, because suddenly you will see, oh, half of the pins are just ground, so I don't really need to care about how I'm going to connect them, because it's going to be super simple. And very similar, you can, for example, apply the color also on the 3.3 volt power net. You will immediately see which of the pins are connected to the layer 2, because there is the power, and it will be super easy to connect them. And you can also apply color on different kind of nets, but at least the ground net is super useful. Now the track width. And this is a very interesting topic, because very often track width needs to be calculated. I don't know how he came up the width for all these tracks, but I need to say he used, or his power tracks are a little bit wider than all the other tracks. So this is good, okay? Power tracks should be wider. As I said, I don't know how he came up with this width, but for this kind of board, for this kind of currents, 30 mil will be okay. When you are doing PCB layout, very often you will find out that powers are routed through polygons or copper pores. I think maybe he didn't know exactly how to use the polygons, because everything is only routed through tracks. So maybe that's why he used tracks. But so let's go back how to calculate the track width. For power, there are online calculators where you can put maximum current, which is going to flow through your tracks, and then it will suggest what should be the minimum width of your track. So be very careful about this. And about the track width for digital signals, standard digital signals, this width needs to be calculated based on the stack up and based on the required impedance. Very often for standard digital tracks, the impedance is 50 ohms. Remember 50, okay? That's what is important, the number 50. Again, I don't know how he come up with the track width for this, but I think this may be 10 mils. It may be just like standard default value for the track width. I know he didn't really calculate it because he didn't tell me what kind of stack up I should use when I will be ordering this PCB. If you would like to learn more how to calculate the track width based on the stack up, I created a number of videos, but usually PCB manufacturer, they will have a calculator where you select the stack up, you know, how far each layer is from each other and how thick these layers are. And based on this, you tell, I would like to have 50 ohm impedance, and it will calculate what width you need to use on what layer. Now, there is something tricky about this, or something how I normally do this kind of, or what is my approach to deal with this track width. Normally, I start routing these standard tracks with a width, for example, 10 mils. But when I finish my layout, I will go to PCB manufacturer website. I will calculate what should be the width for all these standard tracks. Usually it should be less, for example, 6 mils. And then in my PCB, I will select all the tracks, all the standard tracks, which should be 50 ohms. I will select them through a filter. It's very simple. And then I will change the width, all of these selected tracks, to 6 mils, for example. But to be able to do this, you need to be sure that these 10 mil tracks are only the tracks which should be routed by 50 ohm impedance. You really don't want to use 10 mil for power tracks, because then you would be making the power tracks thinner by the end of the layout. And when we have a look here, you can see this is a power track, and when he's connecting this 3.3 volt to the microcontroller, here he is using 10 mil track. Even for this ground, you can see he is using 10 mil track. So I wouldn't do it this way. For the powers, I would use different width. What you can do, you can put here, let's say 10.1. Okay, it's different. It means when you will be using filter based on the track width, then you can equal, yeah, then you will be sure that the power tracks will not be selected. In this case, if I apply this, you will see that also these power tracks are selected because they have 10 mils. This is very specific for the way what I'm using for when I do PCB layout, but I think it is very, very useful. So you should not be using same width for the power tracks and for the standard 50 ohm tracks. Okay, I would maybe initially I would route it with 10 mils, this, and I would route this with 10.1 mils. And by the end of the layout, I would select all these 10 mils tracks and change them, for example, to 6 mils, to the value which is calculated based on specific PCB stack up. And when we are talking about PCB stack up, I would like to highlight that he used 4-layer PCB. Well done, okay? Many people starting with hardware design, they would like to keep price very low, so they go for 2-layer PCB because that's the cheapest one. But if you are starting with hardware design, it is much easier to keep high quality signals on 4-layer PCB than keeping high quality signals on 2-layer PCB. 2-layer PCB may be very difficult to route, okay? And there is no like big difference between 2-layer PCB price and 4-layer PCB price, especially for this kind of small PCBs. There is no big difference. So if you are starting with hardware design, my recommendation is don't use 2-layer PCBs, use at least 4-layer PCB and use at least one solid ground point as what he used here in this case. We can speak a little bit about vias because again, when you are designing your board, you need to come up somehow with the dimensions of the vias what you are going to use. So he used these 24 and 12 mil, and I don't know how he come up with these numbers. Maybe these are default numbers, or maybe from tutorials. But these are good dimensions for a via. So you can have also smaller vias, but smaller via can make your PCB more expensive. And in this case, we don't really need smaller vias. So I'm very happy with this via what he used. Now let's talk about placement, because placement, component placement in PCB is very, very important. And I really like he placed the components in PCB based on the placement in schematic. So very often when you are drawing schematic, you should know what components you would like to place close in your PCB. Let's start with something simple like these components around this LED. So if we select these two components, they should be together in PCB. And here they are. It's in this situation for this LED, it's not important where exactly we will place this resistor, but there are some circuits where it is super important. For example, for regulators like this. Yeah, these components, they should be placed very close to each other. So I'm going to select them and let's have a look. Here they are. Perfect. Okay. Or decoupling capacitors. Yeah, do you remember the decoupling capacitors? Here they are. Each power pin should have a decoupling capacitor placed close to this power pin. So when I select these decoupling capacitors, we should see they are all around the microcontroller and they should be close to power pins. This is a power pin. Okay, you can see power pin, decoupling capacitor. Here is a power pin, decoupling capacitor. Power pin, decoupling capacitor. But this is something unusual. Here, these two components, they are sharing this ground via. So what is this? I'm going to have a look. It's this 4.7 microfarad capacitor, important capacitor, which should be placed close to this pin number 30. So we can double check. Here is pin number 30. So the capacitor is placed close, but I wouldn't share this via. When you are doing PCB layout for power pins, ideally you would like to use at least one via per power pin, power and ground pin. Okay, ground is also power. At least because some powers, they may carry higher current, so you may need to use more vias because there is a limit how much current a via can carry. For example, let's say 1 amp in this case. And there are calculators. If you are not sure how much current a via can carry, then you can use a calculator, it will tell you. But generally, you really don't want to share vias between power pins, especially here in this case. We have big ground plane. There is no need to share this ground via. There is also a lot of space. So I would place one via here and connect this pin directly to via. Then I would disconnect this and connect this path directly to this via. That's very, very good practice. Remember this, okay? At least one via per power pin or per ground pin. And here, oscillator or crystal, same, okay? Here you can see ground pin, ground pin, ground pin, ground pin. Okay, they don't share one via, but it's not really necessary to connect all these together. You can disconnect this, okay? You can just simply connect this path to this via. You can place a via close to this path and connect it, connect this path to this via and connect this path to via. Do not use this connection, do not use this connection, do not use this connection. Each path connected to each own via. I like this crystal is connected or placed close to the microcontroller, so we can keep these tracks as short as possible. So this is good. And now I'm going to confuse you, because I just told you we would like to have one via, at least one via per power pin. So we have one via here, we have one via here, but this is output from a regulator, and the connection between the some connections on your PCB, and this is one of the special connections. These special connections, they need to be connected as good as possible. The connection between the output of the regulator with the output capacitor needs to be the best. And the best connection is on the same layer. So when we have a look into schematic, this is the regulator, this is the output capacitor of the regulator. This is the regulator, this is the output of the regulator, this is the output capacitor. This connection here, it has to be as good as possible. It means ideally on the same layer. Connect these two pins on top layer. Do not use vias. Why? Because vias in this case will introduce inductance, which is not the best for power delivery. When we have a look here down, this is good connection. All these pins, they are directly connected on top layer, and then it goes inside. When I'm doing a layout for power supplies, and when I'm connecting the power output from the power supply, very often I use multiple vias, even if the current which is going to be carried here is not going to be very high. I still would use multiple vias, because it's a good habit. So instead of one via, maybe I would place here 4 vias. But there is bigger problem here around this regulator. This via will not be problem. The problem could be that there is no heatsink area here. I already mentioned, I think, in the previous video, that these regulators, they can get very hot, especially if this input voltage is high, and if the current what we will be driving from here will be high, then this chip can get very, very hot. And to cool it down, here we should have big copper area, okay? And here is no copper area, just these 2 small tracks. No. It may work perfectly fine, but if this Arduino, if this board is going to be powered up from this input voltage, and if we plug in some boards here, and this board are going to use this 5 volts or this 3.3 volts, this chip can get really, really hot. Really, I mean, it can really happen. It's not like theoretical situation. If we only power up this microcontroller, then probably everything will be working fine and this will not get hot. But if you add more devices driving more currents and this input voltage is high, it will get hot. So this is bad. Here should be bigger area. On this side, maybe we don't need to create very large copper area here. because we have 3.3 volts inside of the PCB, but we would need to place multiple vias, maybe even like 12, 8, 10, 12 vias here. So the heat from this chip can go inside of our PCB, and it can be spread on 3.3 volt layer. You remember, yeah, the 3.3 volt layer is here. Layer 2 is the 3.3 volt layer, very large plane on the layer 2. So multiple vias on power output, connection, direct connection between the output and the output capacitors, and be aware of the heat for power supplies. Very important. And when we are talking about vias, there is something what I would like to mention. It's not maybe important for beginners because it can confuse them, but I would like to mention this because it is important for more advanced designs, and it's related to the 3.3 volt power plane which is on layer 2. So basically, in these places where we are changing the tracks going from top layer to bottom layer or from bottom layer to top layer, in these places we should control the fields and the return currents. Basically, we should control how the signals are changing the layers in these places. And when we use as the second layer 3.3 volt and the third layer ground plane, then it may be quite difficult. And in these places, for more advanced PCBs, we would like to place stitching capacitors. And in case we would like to have a big ground plane on layer 2 and big ground plane on layer 3, then we would only need to use something what is called stitching vias. Basically, vias which will be connecting the the ground plane on layer 2 with the ground plane on layer 3. And basically, this via would help to control how the signals are flowing in these areas when they are changing layers. If you would like to learn more, I created a number of videos on this topic, and also there are very nice animations which will help you to understand basically what is happening and why this can be useful. But for this kind of PCB, don't worry, okay? PCB will work perfectly fine even if you don't really control the signal flow in these areas where these signals are changing the layers. Everything will be fine. But I wanted to mention this because you know, you need to be aware of these kind of things what are happening in PCB. And there is more to talk about vias and power pins. For example, this. Can you see this? And I think, you know, he is a beginner. He never designed any board before, so he probably doesn't know that when we have ground plane inside of our PCB, then we don't have to connect through-hole pins through additional via. Okay, so this is not necessary because inside of the PCB, if we go on layer 3, which is ground plane, you can see this pin, through-hole pin, is already connected here through this thermal relief. And same for power. If I go down here, this is ground, but this is power. So here he's also using a via, but this 3.3 volt through-hole pin is already connected on this layer 3 to this 3.3 volt power plane. Okay, you can see here are the connections, thermal relief connection. And when we are talking about this thermal relief, it's something what is very useful. And I think he used probably just default values. This looks like maybe 10 or 8 mil track. Very often I make this thermal connection a little bit wider. And we use thermal connection because when we will be soldering these pins, if there is no thermal connection, sometimes it may be very hard to solder these pins, because what will happen? We were talking about this. This big plane, it can take heat away. It will take heat away from soldering station, and it cool down the tip of the soldering station. That's why it may be very hard to melt the solder and solder this down. For this kind of small PCB, it still should be okay. You can just, use higher temperature and you will be able to solder it. But if you have, I don't know, 12 layer PCB and there are 4 ground planes, then it can be very hard. So that's why we use these thermal reliefs on through-hole power pins. I don't use them on vias. If you have a look, here are ground vias and they are connected directly to the plane. Be careful, sometimes this CAD software, it may have different settings and it may want to connect these ground vias through thermal relief. Usually I will disable it. I will just use direct connection for the vias. And very often I only use this thermal relief on ground through-hole pin. I don't use them for power pins very often. And when we mention USB here, there are few things what we can talk about. So first, USB signals or USB tracks should be routed by 90 ohm differential pair impedance. As I already mentioned, this PCB is probably not using any impedance control tracks, so we don't really need to worry about this too much, because this is very short connection. But the proper way to route USB, you should go check the PCB stack-up, then use the impedance calculator, and based on PCB stack-up and based on the required impedance, the track width for this USB signal and this space between these USB signals, it should be based on these calculations. Here I can see this is 8 mil, so it's a little bit different. I don't know why. Maybe it was default for differential pairs, I don't know. And this space, it just looks like space between these paths or something. I'm not sure if it's controlled. What I really like, he kept this as short as possible. So this is very good, especially in cases if you can't control impedance, keep the signals or tracks as short as possible. So this is very good. What we can have a look is if he used or if we define this as differential pairs. So we can go to design, rules, nets, differential pairs. Oh, he did specify 2 differential pairs. So between connector and ESD, and then from ESD to the microcontroller. Good. But I'm not sure what are the rules. So I don't know, I think maybe these are just the default rules which were used to route them. I don't know. And also what I really like, and you need to be very careful about, is how you place the ESD protection and how you connect the ESD protection. So ESD protection for this USB, it has to be placed as close as possible, so this is correct. And the connection needs to be direct. So don't use vias, anything, just direct connection between the pins. Again, this is correct here. Perfect. This is not exactly how USB should be routed, but this kind of connector, there is no other way how to connect it, so it is okay. And also what is interesting, or what you may want to be careful about, is routing here. Because, do you know why? This USB connector, it has metal chassis. And if you have this kind of connectors or this kind of components with metal chassis, when this metal can touch PCB, you may need to be careful. Sometimes it's not possible to find other way, so maybe sometimes you can just route this way because there is solder mask on the top of the track anyway, you know, the green color or red or black color, so there is some kind of isolation and it should be fine. But I wanted to mention this because maybe sometimes you may need to be super careful and maybe you don't want to route under the components with metal chassis. But in this case, everything is good. This is okay, this is also okay, and I think this is also perfectly fine. So for routing USB, perfect. Now let's have a look at clearance. Clearance is the distance between objects in your PCB, and one of the most important distances is the distance between two tracks. So if you go to design rules, then here you can see the settings for this PCB, and the minimum distance between track and track is set to 4 mils. I think this is quite low number. I don't know why he used 4 mils. I don't know actually what are the minimum capabilities for JLC PCB. We can double check. So JLC PCB, I'm going to find it, and we are going to have a look on traces and minimum track width and spacing for multi-layer PCB, because we have 4-layer PCB, is 3.5 mil or maybe 3 mil. So they will be able to manufacture 4 mils, but it is almost on the edge. If it's possible, don't use the values which are on the edge of your PCB manufacturer, because sometimes it can make your board or your PCB more expensive. So I really wouldn't set 4 mils here. And I'm very curious if there is actually something routed with 4 mil clearance, because here this doesn't look like 4 mils. If I go to properties, you can see the grid size is 5 mils. So this would be like 0, 5, 10. So this is more like 10 mils clearance. And I asked about this because this was very interesting. Yeah, in the rules there is 4 mils, but when you have a look, all these tracks here, they are routed with the clearance 10 mils from each other. So he told me when he was doing a layout here around the microcontroller, he used smaller clearance, and it's because these paths, they are very close to each other. So if you would use, if you would be using 10 mils clearance, then it may be hard to take out the tracks from these paths. So here he used smaller clearance, and then once the tracks were outside of the microcontroller, then he used 10 mil clearance. And this is good. I was very surprised he did it this way. So well done for this. When you are doing maybe a little bit more complex designs, then a little bit easier way would be to create or define special areas, for example around this microcontroller, and then specify special rules, for example 6 mils in this area. But if you are doing like very simple designs, you can just switch between the rules, it's fine. But be careful, okay? Be very careful. For example, I noticed up here these vias are quite close to the board edge. So this is the end of our board. And when your PCB is manufactured, the machines, they have tolerances. So this drilling machine, which is going to make hole for this via, will have tolerance. Tolerance, it means it can move a little bit. It's not 100% accurate. Also, the milling machine, which is going to mill the edge of this PCB, is going to have tolerance. So the clearance for PCB manufacturing around the edges of the PCB is usually a little bit bigger than the clearance inside of the PCB. In this case, I'm very sure they will be able to manufacture it because they manufactured the PCB. So this is not so close to the edge, but still, you know, here is a lot of space. Then maybe I wouldn't place the via here close to the edge. I would maybe place it here. Yeah. Be careful about the capabilities of your PCB manufacturer. You need to know what they are able to manufacture and then set up the rules for your PCB based on their capabilities. We are almost finished. What we can do, we can also have a look at the most critical signals on this PCB. So which is one of the most critical signals, do you know? Reset. I'm going to zoom in here, select this switch, and we can have a look. So this is the reset signal. I'm going to hide all the other layers. Reset signal is very important because it can reset your board. So you would like to have all the other tracks routed away from the reset signal. You don't want to have any crosstalk. You don't want to pick up noise from the other tracks. So as you can see here, all the other tracks are routed away from reset. So there is nothing routed close to this reset signal. So this is good. This is very good. Maybe here, this is the oscillator track. I really don't know why they designed the microcontroller the way that the reset pin is close to the oscillator pin. I have no idea. But I would try to move this reset track away from this oscillator track. As it is now, I'm very sure it's going to work perfectly fine. This distance is very short, so it's okay. But there is space to improve it. It's very simple to just move this decoupling capacitor maybe a little bit down and move this reset signal away from this. Why not? Okay, it's very easy to do, so I would move it away. Also, what I would do, I would maybe not use this sharp corner, and this is just there is nothing wrong with this sharp corner. It's going to work perfectly fine. But when I'm designing PCBs, I would like the PCB look nice. And for me, if I would do it maybe like this way, this would look a little bit nicer. But it's only my own opinion, okay? There is nothing wrong when it is done also this way. It can be. What is the other, or what other critical signals we may have on our boards? Clocks. I think there is clock signal here. Here is clock. So I'm going to select this. We are going to find it. Here is the clock signal on bottom layer. And I can hide all the other layers. Clock signal can create a lot of noise. So maybe you don't want to route other signals close to the clock tracks. Very often when you are doing PCB layout on your PCB, you would like to have bigger space around the clock tracks. So this signal which is here, I would route it a little bit far away from the clock signal, okay? So it doesn't pick up the noise from the clock. I'm going to put it back. And there is this. I already mentioned when I'm doing PCB layout, I really would like my PCB look nice. And especially this is bottom layer. So everyone who is going to hold your PCB, they will see these tracks. It doesn't look nice. If I would be doing this, I would try to make it a little bit nicer for me. Nicer, it means, for example, something like this, okay? And this, maybe move this away, so there is a lot of space between the tracks, okay? And I would make them shorter. I wouldn't go back here. Just as I said, for me it doesn't look very nice, but it's going to work. It's fine. But when someone is holding your PCB, you would like people be like, wow, I like your PCB, okay? And I think that's everything about these critical signals. There are also powers, but we were already talking about powers. If you would like to check them, you can just go to nets and, because he used the plus sign for the power nets, it's very easy to select and find the power nets. All these nets which are starting with plus, they are power nets. So you can just select them and you can double check how they were routed if they are using the wider tracks. But as I said, we were already talking about the powers, so we don't have to check these connections. When I was selecting this header in schematic, I noticed something. So let's go back. And I noticed it is called U4. And when I was doing the schematic review, I didn't point out this. So there are some kind of standard names for components, and usually headers and connectors, the reference designator starts with J or maybe con or something like this, but U is usually for chips, okay, integrated circuits. So that's something what I noticed also in this design. I would correct all these reference designators, okay. The headers, they are not U, they should be maybe J. So this was a small addition to the schematic review. What we can do now, we can also run DRC check. So first let's do it for schematic and let's have a look if there are some errors. So down here DRC, check DRC. There are some warnings and we can ignore this. Even I don't know how to fix this. I have no idea. So I'm going to close this and let's go to PCB. Down here DRC, check DRC and let's have a look. Oh, there is error and it's about these differential pairs. So because these tracks are specified as differential pairs, one of the rules what applies for differential pairs is the maximum difference in the length between these two tracks, between positive and negative track, and that's what is this error about. So in the rules the maximum difference is set to 10 mils, but we have like 31 mils. If we have a look, then the length for this one is 192 and this one is 161. So that's the error. There is not much what we can do to fix it here in the layout. If we would like this, if we would like to have this error gone, then what we have to do, we have to adjust the rule. So instead of using 10 mils, change the rule to 35 mils, and then there would be no errors when you run the DRC check. So I'm going to close this. When you are sending PCB to production, there should be no error. So that's what I would do. I would probably change the rule. So when we run the DRC check, there are no errors. And only what left is to try the PCB. So here is the board, okay, and I already flashed the firmware. Firmware is going to blink with the user LED. So this is the power LED, this is the user LED, and I know exactly what's going to happen because I flashed the firmware, but you can have a look. I'm going to connect power, and it's working. Well done. I'm very impressed because, you know, there are no cuts. I mean, I didn't cut any tracks or anything on the PCB. There are no wires. I didn't have to solder any additional wires, and it looks like it's working. There were some small details which I pointed out in the schematic review and in the PCB review, but for very first board, this is very well done. Fantastic job. And that's everything. If you haven't seen the part 1 schematic review, the link to the video is in the description. Also, if you would like to learn more about how to design boards, check out our online courses. You will find everything important there, from basic board design up to advanced board design and high-speed PCB layout. We have courses in Altium, Cadence, KiCad, and also courses covering many different topics, for example, FPGA, EMC, measurements, and so on. Visit our website at fedevel.com. That's all for this video. Thank you very much for watching, and don't forget to leave your comments. See you in the next video. Bye!